Welcome to class number 2, session number 2. Fabrication of nanoscale structures or devices can be achieved either by top-down approach or by bottom-up approach. Bottom-up approaches seek to have smaller components built up into more complex assemblies, while top-down approaches seek to create nanoscale devices by using larger, externally controlled ones to direct their assembly. The top-down approach often uses the traditional workshop or microfabrication methods where externally controlled tools are used to cut, mill, and shape materials into the desired shape and order. Micropatterning techniques such as photolithography and inkjet printing belong to this category. Bottom-up approaches, in contrast, use the chemical properties of single molecules to cause single molecule component to, first of all, self-organize or self-assemble into some useful conformation, or, secondly, rely on a positional assembly. These approaches utilize the concepts of molecular self-assembly or molecular recognition. Such bottom-up approaches should, broadly speaking, be able to produce devices in parallel and much cheaper than the top-down methods, but could potentially be overwhelmed as the size and complexity of the desired assembly increases. Focused ion beam, also known as FIB, is a technique used particularly in the semiconductor industry, material science, and increasingly in the biological field for site-specific analysis, deposition, and ablation of materials. FIB systems operate in similar fashion to the scanning electron microscope, which we have abbreviated so far by SEM, except the fact that FIB systems uses a finely focused beam of ions, usually gallium, that can be operated at low beam currents for imaging or high beam currents for site-specific spattering or milling. As the diagram on the right side of the slide shows, the gallium primary ion beams hits the sample surface and spatters a small amount of material, which leaves the surface as either secondary ion or natural atoms. The primary beam also produces secondary electrons. As the primary beam rasters on the sample surface, the signal from the spattered ions or secondary electrons is collected to form an image. At low primary beam currents, very little material is spattered, and modern FIB systems can easily achieve 5 nanometer imaging resolution. At higher primary currents, a great deal of material can be removed by spattering, allowing precision milling of the specimen down to a sub-micrometer or even to a nanometer scale. If the sample is non-conductive, a low-energy electron float gun can be used to provide charge neutralization. In this manner, by imaging with positive secondary ions, using the positive primary ion beam, even highly insulating samples may be imaged and milled without a conducting surface coating, as would be required in SEM. Following is a short video that demonstrates the FIB operating along with animated presentation. Enjoy. Other videos demonstrating the capabilities of the FIB in the fabrication of nanoscale materials or devices could be seen in the attached link. Now we will move to the photolithography approach. Photolithography, also termed optical lithography or UV lithography, is a process used in the microfabrication to pattern parts of a thin film or a bulk of a substrate. It uses light to transfer a geometric pattern from a photomask to a light-sensitive chemical photoresist, or simply called resist, on a substrate. A series of chemical treatments then either engraves the exposure pattern into or enables the position of new materials into the desired pattern upon the materials underneath the photoresist. The main, if may not all, the stages involved in the typical photolithography process are, first and foremost, cleaning. This procedure removes organic and inorganic contaminations that are present on the wafer surface, either by wet chemical treatment or dry approaches, mostly using plasma. Photoresist application. The wafer is covered with photoresist by spin coating. A viscous liquid solution of photoresist is dispensed onto the wafer, and the wafer is spun rapidly to produce a uniformly thick layer of few nanometers or to few micrometers. The photoresist coated wafer is then pre-packed to dry off excess photoresist solvent, typically at 90 centigrades to 100 centigrades for 30 to 60 seconds on a hot plate. The next stage is the exposure and the developing. After pre-packing, the photoresist is exposed to a pattern of intense light. The exposure to light causes a chemical change that allows some of the photoresist to be removed by a special solution called developer by analogy with a photographic developer. Positive photoresist, the most common type, becomes soluble in the developer when exposed. On the other hand, the negative photoresist shows is soluble in the developer when the unexposed regions are exposed to the same solution. A post-exposure pre-pack is performed before developing, typically to help reducing standing wave phenomena caused by the destructive and constructive interference patterns of the incident light. The resulting wafer is then hard-packed to solidify the remaining photoresist, to make a more durable protecting layer in future ion implementation, wet chemical etching, or plasma etching. The next stage in this microfabrication process is called etching. In etching, a liquid, or so-called wet, or plasma, called also dry chemical agent, removes the uppermost layers of the substrate in the areas that are not protected by the photoresist. In semiconductor fabrication, dry etching techniques are generally used as they can be made of anisotropic in order to avoid significant undercutting of the photoresist pattern. This is essential when the width of the features to be defined is similar to or less than the thickness of the material being etched. The next stage is called deposition of thin films. In other cases, actually, target material is deposited on the surface. This layer covers the remaining resist as well as the parts of the wafer that were cleaned of the resist in the previous developing step. The next step is called photoresist removal. After a photoresist is no longer needed, it must be removed from the substrate. The sacrificial material, namely the photoresist, is washed out throughout together with parts of the target material covering it, and in this case only the material that was in the holes and having a direct contact with the underlying layer stays. This usually covers a liquid resist stripper, which chemically alters the resist so that it no longer adheres to the substrate. So far, photolithography is comparable to a high-precision version of the method used to make printed circuit boards. Subsequent stages in the process have more in common with etching than with lithographic printing. It is used because it can create extremely small patterns. It affords also exact control over the shape and the size of the object it creates, and because it can create patterns over the entire surface cost-effectively, this technique is highly recommended. Its main disadvantages are that the technique requires a flat substrate to start with. It is not very effective at creating shapes that are not flat, and it can require extremely clean operating conditions. Following is a short video that demonstrates the photolithography process along with animated presentation. Enjoy. We will move now to electron beam lithography. Electron beam lithography, which abbreviated as EBL, refers to a lithographic process that uses focused beam of electrons to form the circuit patterns needed for material deposition on the wafer. In contrast with the optical photolithography, which uses light for the same purpose. Electron lithography offers higher performance resolution than the optical lithography because of the shorter wavelength possessed by the 10 to 50 kilo electron volt electrons that are employed in this process. Given the availability of the technology that allows a small diameter focused beam of electrons to be scanned over a surface, an electron beam lithography does not need masks anymore to perform its task. An electron beam lithography system simply draws the pattern over the resist wafer using the electron beam as its drawing pin. Thus, the electron beam systems produce the resist pattern in a serial manner, making it slow compared to the optical system. A typical electron beam lithography process and system consists of the following parts. The first, an electron gun or electron source that supplies the electron. Second, an electron column that shapes and focuses the electron beam. Third, mechanical stage that positions the wafer under the electron beam. Fourth, a wafer handling system that automatically feeds wafers to the system and unloads them after the processing. And finally, a computer system that controls the equipment. The resolution of the optical lithography is limited by diffraction, But this is not the problem for the electron lithography. The reason for these short wavelengths exhibited by the electrons in the energy range they are being used in the electron beam lithography systems. However, the resolution of an electron lithography system may be constrained by other factors such as electron scattering in the resist and by various aberrations in the electron optics. Just like optical lithography, electron lithography also uses positive and negative resists. The resolution achievable with any resist limited by two major factors. The first is the tendency of the resist to swell in the developer solution, and the second, electron scattering within the resist layer. The primary advantage of electron beam lithography is that one of the ways to beat the diffraction limit of the light and makes features in nanometer region. This form of maskless lithography has found wide usage as a photomask making used by the photolithography, low volume production of semiconductor components, and also for a lot of research and development. The key limitation of electron beam lithography is thorough output, namely, the very long time it takes to expose the entire silicon wafer or glass substrate. A long exposure time leaves the user with a broad beam drift or instability that may occur during the exposure. Also, the turnaround time for reworking or redesign is length in an unnecessary way if the pattern is not being changed the second time. The left side images demonstrate production level high-resolution electron beam lithography of lines and dots formed in a resist. In this example, 20 nanometer sized features were delivered and have a pattern transfer capability for a wide range of materials. Nanometer level-to-level alignment accuracy is made possible by the in-house software and maker design that's used in these system and samples. The right side image includes a single silicon nanowire that is contacting by two adjacent electrons to enable measuring the silicon nanowire's electrical properties. With this, we come now to the end of class number 2, session number 2. Thank you.